Okay, so we will continue with Fourier analysis. What you have seen so far is the Plancherel Theorem, which says if I have a function in L2, its Fourier transform is also in L2 and the L2 norms are same, right. Moreover, it is a unitary operator. So, starting from L1, we extended the definition of the Fourier transform to L2 and proved that it is a unitary operator. Okay. So, we continue with studying the properties of the Fourier transform. Okay. So, let us recall that if the function is in L1, then the Fourier transform is a bounded function. Moreover, it vanishes at infinity, right. It is a continuous function vanishing at infinity. And if the function is in L2, then the Fourier transform is in L2 and the norms are same. Okay. So, naturally question is what happens with other LP spaces, correct. So, that is what we will do in the next. So, this is called the Hausdorff inequality. In the next two lectures, we will prove what is known as the Hausdorff inequality, which tells you function is in LP, its Fourier transform is in LQ, okay, where Q is 1 by P plus 1 by Q equal to 1. This we will do. So, there are several proofs of this. These are classical results and there are several proofs. So, we will do this using what is known as Riesz-Thorin Convexity Theorem. It is an interpolation theorem. It is a purely functional analysis result, okay, and then we apply it to the linear operator Fourier transform. That is what we will do. Okay. So, let us start. But how do we define the Fourier transform for LP functions? So, we start with L1 and L infinity and so on. So, I have let us say script f. So, this takes, we know that it takes L1 of Rn to C0, but let us say L infinity, right. In fact, it goes to C0 by Riemann-Lebesgue lemma, right, we know that. Then we also have script f now extended to L2, right, to L2. Here we have a very strong result which is Plancherel, right. So, this is a unitary operator. Okay. We are going to extend it to functions in LP where P is between 1 and 2. Okay. So, here we need some things about LP spaces which you already know, but may not have actually looked at it from that point of view. LP for P between 1 and 2 is contained in the sum of these two spaces. Okay. What does that mean? If I take an F in LP, okay, 1 strictly less than, okay, for 1 and 2 we already know the definition, right. So, keep things in mind. Here we have an integral definition which makes sense because F is in L1. Here we have an extension as a unitary operator. Okay. There is no integral definition here except for functions in L1 intersection L2. The integral may not exist, but you have a definition, well defined operator, right, unitary operator. Now, I take a function in LP where P is between 1 and 2, I can split it so that one piece is in L1, the other piece is in L2. Okay, I will write down what it is. Then this definition allows me to extend the Fourier transform to all LP. But then we also have to see where it lands, right, where does it go, just like L infinity L2, which LP does it go to. Okay. So, let us do the splitting first. Okay. So, write F as let us say F1 plus F2. Okay. What is F1? F1 is f of x. So, F1 at x is f of x times indicator of the set where, okay, so maybe y such that mod f of y is greater than 1. Okay. So, this would be in L1, okay, and F2 f of x times whatever is remaining, right. So, y such that mod y less than or equal to 1. Okay. This is going to be in L2. So, this is the splitting, right, F1 and F2. F1 is f where f is greater than 1. Okay. So, remember it is in LP, right, for P greater than 1. This set has finite measure, right. If f is in LP, any LP, where f is bigger than 1 should have finite measure, otherwise the integral is already infinite. So, this is restricting f to a set of finite measure, but it is in LP, so it will be in L1, right, finite measure. Here f2 is f where f is less than or equal to 1. So, f is, this is bounded, right, because it is restricted to the set where it is less than or equal to 1. F is in LP, and if it is in LP and it is in L infinity, it will be in all the, right, but P is less than 2. So, it is in LP, L infinity, so it will be in L2. So, that is in L2, right. So, given a function in LP, I can split it into two parts, one belongs to L1, other belongs to L2, okay. Not just L1 and L2, you can do this for any P and Q, okay. So, if I take P, Q and I take an LR function, I can write it as a function of LP function and LQ function. Now, I can define the Fourier transform because F1 is in L1, there is no problem. F2 is in L2, no problem, you can define the Fourier transform. So, Fourier transform of f can be defined to be f1 hat plus f2 hat, right. So, define. So, I am trying to extend it to LP functions, right. So, define the Fourier transform of f to be f hat equal to f1 hat plus f2 hat, right. So, this extends the definition to LP, but you still have to prove it is well defined and what are the other properties and so on, okay. Well, this much is fine, but how do you know this is well defined? What do I mean by well definedness? I can use some other functions here to split f, right. There may be several such. For example, instead of 1 I can take 10, okay, or there may be completely different functions, right, which are in L1 and L2 whose sum is f. So, how do I know that I am going to get the same definition? I may get different things, right. So, well definedness, right. So, let us see why it is well defined. So, let us take another splitting, okay. So, suppose f is equal to G1 plus G2, where G1 is in L1 and G2 is in L1, right. I want to say I will get the same chap here, right. So, that is what well definedness means, okay. So, f is equal to G1 plus G2, but f is also equal to f1 plus f2, right. So, what does this tell me? This tells me that f1 plus f2 is same as G1 plus G2, right. Well, there will be always an almost everywhere statement, right, because we are looking at LP functions and so on. But well, let us combine these two. So, I have f1 minus G1 equal to G2 minus f2, again almost everywhere, right, no problem. But what is the advantage? f1 is in L1, G1 is in L1, f1 minus G1 will be also in L1, okay. So, this is a function in L1. G2 is in L2, f2 is in L2, G2 minus f2 will also be in L2, right. So, here is a function in L1, here is a function in L2. So, both the functions are in L1 intersection L2, okay. So, instead of saying, okay, and there everything is well defined, there is no problem, right. We have a nice definition of Fourier transform on L1, we have a nice definition of function on L2. So, I can take Fourier transform, okay. So, this would be same, right. But Fourier transform is a linear operator. So, f1 and g1 are in L1. So, f1 minus g1, if I take the Fourier transform, what will I get? f1 hat minus g1 hat, okay. So, I will use the magical properties of the board to avoid writing it again and again. So, this is simply f1 hat minus g1 hat. Here both are in L2, it is a unitary operator applied to g2 minus f2. So, that will be G2 hat minus F2 hat, okay. So, that is fine. Well, we will still have equality almost everywhere, well at least as functions in L2. So, this is in equality in L2, okay, which is same as saying it is almost everywhere, right. So, in particular almost everywhere. So, now I can bring it back, right, take F2 to the other side, G1 to this side. So, this tells me F1 hat plus F2 hat equal to almost everywhere, and that is all we wanted, right. I started with some splitting F1 plus F2, define the Fourier transform to be this. I wanted to show that it is independent of the splitting, right. So, whatever splitting I take such that G1 is in L1, other one is in L2, okay. What do I have? I have that F1 hat plus F2 hat, which is the definition of the Fourier transform in LP, is equal to G1 hat plus G2 hat, where this was an arbitrary splitting in the same manner, right. So, this tells me it is well defined, right. Whatever splitting I take for F as a L1 and L2 function, I will get the same function, okay. So, this proves the well definedness. So, we can take this as the definition, right. So, you can, does not have to be this splitting, you can stick to whatever splitting you want, but any of those splittings will give you the same definition, okay. So, now the Fourier transform, even though it is defined only on L1 and L2, now it is defined on all LP functions, okay. So, this, so let us say this extends the definition, this extends the definition of Fourier transform to LP functions, right, LP of Rn for 1 less than to p less than or equal to 2. 1 and 2 we already know, now we have extended to in between, right, for all p between 1 and 2. Okay. Our aim is to study the Fourier transform on LP spaces just like these results, where do you go, right. What do we know about the Fourier transform? Looking at this, you already know F1 since it is in L1, F1 hat is a continuous function, right, it is a continuous bounded function. F2 hat, F2 is in L2, so F2 hat is also in L2. So, this is a continuous function, bounded continuous function plus an L2 function, right. This much we can read off simply by looking at it. That is not, I mean that is not the only thing we know. Whatever we are going to write down will tell you that this actually lands you in certain LP space, okay. So, this is a rather well known result called Hausdorff-Yang theorem or inequality or whatever, okay. If F belongs to LP of Rn, 1 less than to p less than to 2, well I will stick to 1 strictly less than p strictly less than 2, because 1 and 2 we have already dealt with. We have Riemann-Lebesgue lemma and Plancherel theorem. Then the Fourier transform belongs to LQ, where q is the conjugate exponent, okay, 1 by p plus 1 by q equal to 1. And not just that it lands in LQ, the operator is bounded, and if you know, okay, where C is independent of F. Okay, so that is called a Hausdorff-Yang inequality. So let's repeat. If F is a function in LP, then F hat is in LQ, where 1 by p plus 1 by q equal to 1. That is what happens at the end points, right. When p is 1, q has to be infinity. When p is 2, q has to be 2, right. So, for L1 and L2 we already know this result. Hausdorff-Yang tells you that it actually happens for all LP for p between 1 and 2, okay. P greater than 2 is a different matter, okay, that is a different ball game, we will not get into that right now. So, what we are going to do is to attack this inequality as we will do in function analysis, we have a linear operator which is bounded from one LP space to the other space. Similarly, the same operator, right, it is the same operator here which is bounded on some other LP space. We want to interpolate, we want to get results in between, okay, that is what interpolation tells you, and that is called the Riesz-Thorin convexity theorem. Okay. So, proof of this will be done, we will use Riesz-Thorin convexity theorem, okay, or interpolation theorem. Interpolation theorem. Okay, so I'll state it, and we will prove the Riesz-Thorin interpolation theorem. That requires some complex analysis, something like the maximum modulus principle for a strip. So, it is called the 3 lines lemma. So, in this part of the lecture we will I'll state what Riesz-Thorin convexity theorem is, and I will prove that auxiliary result which is needed, which is the 3 lines lemma from complex analysis. You will see how complex analysis enters into the picture. Riesz-Thorin proof is a very nice proof. It also tells you the power of complex analysis in various other subjects, and then we will use that to this particular linear operator. So, Riesz-Thorin convexity is a general theorem about bounded operators on LP spaces. Okay, we can apply it to convolution, for example, we will get some inequality. I will write down that those examples. Okay, so let me state Riesz-Thorin in full generality, but we need some definitions before that. Okay, so let's start with a space X, okay, a sigma algebra of subsets of X, and a sigma finite positive measure, right. This is what you call a measure space, right. So, this is a sigma finite measure, positive measure, okay, positive. Similarly, we have another space Y, sigma algebra on Y, and a sigma finite positive measure. Okay, we have two, and we have LP spaces, right, LP of mu and LP of LQ of nu. Okay. So, P between 1 and infinity. So, I'll write LP of mu and LQ of nu. Okay. So, if T is a linear operator from LP of mu to LQ of nu, okay, it does not have to be defined on all of LP, it is enough it is defined on a dense subspace like the symbol functions, for example. Okay. So, this is a linear operator from this LP to this, like the Fourier transform. Okay, keep that in mind as your T is bounded. What does that mean? That means if I take a function here, apply T, I land here, take the LQ norm, that will be less than or equal to LP norm of the function, right, times a constant which is the norm of T, right, bounded. That means, so norm of TQ, so LQ norm is equal to some constant times LP norm of F, right. Then we say T is strong, then okay. So, this is just a nomenclature or notation, okay. So, then we say T is type PQ, okay. So, this is all you have to remember, linear operator is type PQ if it is bounded from LP to LQ, okay. So, there is nothing which you do not know here, okay, something which you are already familiar with. I am just using a new term called type PQ, okay. So, Riesz-Thorin is about linear operators which are type PQ for two different values of P and Q. So, I have two different values of P, two different values of Q. I have boundedness from one P to one Q, right. I want to say it is bounded in between. if I have boundedness on the endpoints. So, that is what is called Riesz-Thorin interpolation theorem. Okay. So, suppose, so there are certain things which I am not saying. If I know that it is defined just like what we did with Fourier transform. Okay, if I know that it is defined on L1 and I know it is defined on L2, then it is defined in between, right? Because any function in between is a sum of functions at the endpoints. Okay, so that extension is always there. Question is about boundedness. Okay, so let T be a linear operator. Which is type, okay, so P0 Q0 and P1 Q1, okay, where all these are in between 1 and infinity. Okay, so where 1 less than 2, P0, P1, Q0, Q1, okay, less than to infinity. So, we have those sigma finite measure spaces, remember that. I am not writing the x, y, mu, nu and so on. Then T is of type P sub small t, Q sub small t, okay, where. So, this is the conclusion we want, right. It's bounded between two LP spaces, then it is bounded in between, okay. So, which P goes to what Q, right, that has to be specified. Okay. So, T is of type PTQT, where 1 by Pt equal to 1 minus T by P0 plus T by P1, 1 by Qt. This is all very similar. Okay. So, there will not be any confusion once you understand what this says. Plus T by Q1, 0 less than to T less than to 1, and the norm of T from LPT to LQT is bounded by M0 to the 1 minus T, M1 to the T, where M0 is the P0 Q0 norm of T and M1 is the P1 Q1 norm of T. Okay, I will explain everything. Okay. So, let us go through the statement. I have a linear operator which is bounded from LP0 to LQ0, right. So, let us write down T is from LP0. So, remember there is some measure mu and some other measure mu, right. So, this is bounded, right, bounded, and the norm is, so this is the norm from P0 to Q0, this is less than or equal to M0, right, that is the constant we have. So, at the 0 we have P0, Q0 and M0, and similarly it is bounded from LP1 mu to LQ1 nu bounded, and the corresponding norm P1 to Q1 norm is less than to M1, that is assumption. Okay. Then what we are saying is it is bounded in between. So, what does that mean? So, here everything is written in terms of 1 by P, okay, 1 by P and 1 by Q. So, let us draw some pictures. So, this is 0 0, okay. So, let us say this is 1 0. So, I have this square, this is 1 1 0 1, okay. So, this is the square for 1 by P 1 by Q. Remember everything is between 1 and infinity. So, 1 by P and 1 by Q will be between 0 and 1, right. So, any coordinate here will give me a 1 by P and 1 by Q, right, P and Q between 1 and infinity. So, what does this say? This says that I take a point P0 Q0, there it will be 1 by P0 1 by Q0. So, let us say this is the point, okay, 1 by P0 1 by Q0, Okay. And similarly, I have another point P1 Q1, on the square it is 1 by P1 1 by Q1. So, let us say 1 by P1 1 by Q1. Okay. So, T is of type P0 Q0, that means it is bounded there. Similarly, T is type P1 Q1. Then T is type Pt Qt for every T between 0 and 1, where Pt and Qt are defined like this. So, how are they defined? So, if you look at this, this is the line joining 1 by P0 and 1 by P1, right, and this is the line joining 1 by Q0 and 1 by Q1. So, if I put together this is simply the line joining 1 by P0, 1 by Q0 to 1 by P1, 1 by Q1. So, what you do is you simply join this line. So, you get one line, you take any point here, you will get a 1 by Pt, 1 by Qt, and T is bounded there. Okay, that is all the theorem says. So, the in between Pt and Qt are defined by this relationship. This relationship is linear, but in 1 by P and 1 by Q. So, if you look at our Hausdorff Young, we have one, right, we have 1 infinity at this point, right, L1 to L infinity. At 2 we have 2 2, right. So, let us try to understand what this is in our square. Okay. So, this is 0 0 and 1 1. Well, 1 infinity will go to, here it is 1 by P, 1 by Q. 1 goes to 1, infinity goes to 0. So, it is 1 0. So, where is 1 0? Here, right, 1 0. 2 2, where is 2 2? Well, that will be half half, right. So, you look at the diagonal and you look at half half. Okay. The convexity theorem say, well, we will see why it is convexity theorem. The interpolation theorem says that if I have this point and this point, then I have this line. What are the points here? This is the off diagonal, right, or the whatever, the opposite diagonal. That is all x comma y such that x plus y is 1, right. So, P will have to go to Q such that 1 by P plus 1 by Q is 1. That is precisely Hausdorff, right. I do not see many happy faces. Let us repeat. If a linear operator is bounded and I have type P0 Q0 and P1 Q1, then T is type Pt Qt, which means it is bounded from LPT to LQT. The important point is what are Pt and what are Qt, right. So, Pt and Qt have a very simple relation between the endpoints P0 P1 and Q0 Q1. How is it related? They are related, if you look at the reciprocals, they are related linearly. Okay. So, there is an explicit formula. If I give you 2 points in the square, you can join the line, and whatever point I take in that line, that will give me a Pt Qt like this, and my T, the operator, will be bounded there. Not just bounded, there is a bound on the norm. We will come to that later. Okay. If we apply this directly to whatever we know about Fourier transform, we will get Hausdorff Young inequality. That is all I want to say. So, let us look at that again. I know that the Fourier transform is bounded from L1 to L infinity, right. So, it is type 1 infinity. 1 infinity as a point in the square becomes 1 0, right, because we are taking 1 by P and n. So, I have this point. Similarly, at 2 I know it is a unitary operator. So, it takes L2 to L2. So, it is type 2 2, right. So, in the square it becomes 1 by 2 1 by 2. Now, the interpolation theorem tells me that you simply join these 2 points, take anything in between, that will give me the Pt Qt. So, if I take any point here, how does the point look like here? Well, these are all, so this line is simply the line x plus y equal to 1. Okay. So, any point here is such that x comma y, x plus y is equal to 1. So, if I write it in PQ terms, it will be 1 by P, 1 by Q such that 1 by P plus 1 by Q equal to 1, and that is precisely this, right, that is the Hausdorff Young. So, if I prove Riesz Thorin, this follows immediately, right, straightforward application. So, our aim is to prove restoring convexity. So, now you see this has nothing to do with the Fourier transform. So, purely functional analysis result, right. I have a operator, I want to know where it is bounded. All right. So, proof uses what is known as 3 lines lemma. Proof needs 3 lines lemma from complex analysis. Okay. So, we'll do that first. Okay, so let's write 3 lines lemma. This is a very nice theorem from complex analysis. 3 lines. Okay, so okay, 0, 1. So let's look at this strip. Okay, so let's call the strip S. All those complex numbers, right, whose real part is between 0 and 1. Okay, so 0 strictly less than real part of Z strictly less than 1. Right, this is a domain in the complex plane. Okay. So let capital F be a function from S closure to complex plane, continuous and holomorphic. Holomorphic means analytic, right? Analytic in S. Okay, we need some assumptions. So let me see if it's bounded. Okay. So F is a bounded continuous function on S closure. So that means the closed strip, okay, the whole strip, it's continuous on the whole closed strip, holomorphic in the interior. Okay, in S, okay, if f of I y less than or equal to m naught and 1 plus I y is less than or equal to m 1, then for any t between 0 and 1, f of t plus I y is less than or equal to m 0 of 1 minus t m 1 of t. Okay. So, supremum over y. Okay. Yeah. So, I'll explain what that means. So, this is like a maximum modulus lemma which you see from complex analysis. If I have a holomorphic function, the maximum is never attained in the interior, right. It is attained at the boundary, but in a slightly more general terms, it tells you that if you know what happens at the boundary in terms of the size of the function, you can say something about the size of the function inside, right. If it is bounded by 1 on the boundary, it is bounded by 1 inside. This says exactly that. Now I have an unbounded domain, so I can't apply maximum modulus directly, but it still says if I know the bound of the function on this line and this line, which is the boundary of the strip, right, then I can say something about the function value inside. Well, what is the function value inside? Look at f of t plus I y. So, you take any t between 0 and 1 and look at the line here, right. So, this is my t plus I y line, right, y going from minus infinity to plus infinity. Then it is bounded by whatever the bounds you get here. So, the bounds you get here is m naught. So, at here it is m naught, at here it is m 1. Then if I take t, I will have m 0 to the 1 minus t and m 1 to the t. Okay. So, that gives me the bound. So, the convexity comes from the fact that if I take the log of this, I will get 1 minus t log m 0 plus t log m 1, which is same as saying the log of modulus of f is a convex function. Okay. That is what this says. So, that is why the convexity. Well, proof of this is purely complex analysis, but we need some auxiliary functions which is not very difficult to construct. So, is the statement clear? I have a holomorphic function here which is continuous up to the boundary. I have bounds on the boundary. I'll have bounds on these lines. Okay, that's why it's called 3 lines, right? You have 3 lines. That's why it's called 3 lines lemma. Alright. So, what we do is first we can assume that these two are 1. Okay. So, consider g of z equal to fz divided by m0 to the 1 minus z, m1 to the z. Okay. Well, so without loss of generality, assume that m0 is positive, m1 is positive. Okay. Because if one of them is 0, you want to conclude that the function is 0, right. This estimate says if f is 0 on one line, then it is 0 everywhere because of this, okay, or f is 0 on this line, it will be 0 everywhere. But to define this function, we need this to be positive numbers. Well, what will happen if one of them is 0? You can put any epsilon here, right, and prove this bound and let epsilon go to 0. Okay, so without loss of generality, we can assume it to be 0. It is assumed to be positive. So this function is well defined. F is holomorphic, and I am dividing by something which is never 0. So that is also holomorphic, right? Remember how is this defined? If I take a positive number a to the z is defined to be e to the a log z, right? Right, this is never 0, right? So this is a nice function, and it's holomorphic, right? All these are holomorphic functions. So g is a holomorphic function and continuous up to the boundary. Okay, there is no problem. So g is holomorphic in S and continuous on S bar, right, the closure. This is just a normalization to reduce everything to 1. Okay, this is something which you would have seen several times in other forms. So let's see what happens at these lines. So our aim is to show that bounds on these lines implies bounds on any line in between, right. So let's see what happens to the new function on the line. So let's look at modulus of g of iy. What is modulus of g of iy? Well, we have f of iy. So modulus f iy by, so iy is the imaginary axis, right. So m0 of 1 minus iy. So I have modulus of m0 of 1 minus iy, and I have m1 iy. Well, what happens here? So this is less than or equal to the bound of f on the imaginary axis. What is that? I have m0, right. So I'll have m0 on the top. What is the denominator? What is modulus of this? That is just m0, right, m0 to the 1 and m0 to the minus iy. Remember the definition. If I have a and so I'll it is no, what did I write? Sorry, I wrote, okay, yeah, that definition was wrong, sorry. It is e to the z times log a, right. I mean, that is what should be the definition. So this is e to the z times log a. Log a is the constant, right. So yeah. So if z is purely imaginary, then e to the z something, that will be e to the something purely imaginary. So modulus is 1, right. So modulus of m1 to the iy and modulus of m0 to the minus iy will be 1. So in the denominator is just m0, this is 1. Okay. So similarly, g of 1 plus iy on the other end of the line, right, this line. On this line, I know f is less than or equal to m1, and then let's see what happens in the denominator. So this is less than or equal to m1 divided by modulus of m0 1 minus z. Any point here is 1 plus iy, right. So 1 minus 1 plus iy will give me a minus iy, right. So it's minus iy and m1 to the 1 plus iy, right. So for any y real, this, so this is 1, this is 1, I have m1, 1. So all that I have done by dividing by this function is I have now a continuous bounded function on the strip whose bounds are 1, right, and I want to prove this inequality where now m0 and m1 is 1, right. So, because of this, right, because if I prove that this is less than or equal to 1, I will have m0 to the 1 minus t and m1 to the t, right. The imaginary parts goes away because modulus is 1. So, this will come out. So, it is enough to prove the theorem for m0, m1, 1. So, that is what we have done by reducing it to the. Okay. So, we have this. So, now define, well, we are going to apply maximum modulus, okay, but we do not have a bounded domain to apply maximum modulus. So, we will cut it off at some place, but then we do not know what happens outside, right. So, what we do is we multiply g with a function which goes to 0, okay, so that outside it becomes small and then we have a bounded domain, apply maximum modulus. Okay. So, define J&Z equal to gz times e to the z square minus 1 divided by n. Okay. So, let us see if that will do. Any other function will do, but we just choose one. So, g now is a holomorphic function in the strip bounded by 1 on the boundary. I have multiplied it with e to the z square minus 1 divided by n. Well, this is a nice continuous holomorphic function. So, it is still a holomorphic function inside the strip continuous up to the boundary. Okay. What happens at the boundary lines and what happens as y goes to infinity we will see. So, let us look at modulus of g and z. Okay. So, modulus of g and z, this is equal to mod gz, we know it is less than or equal to 1 times, well, what is this? This is e to the, if I write x plus iy, then I have x square plus 2i xy minus y square minus 1, right, divided by n. If I take the modulus of this, well, I will have e to the x square, that stays, this gives me modulus 1, I have minus y square minus 1 divided by n, right, that is how it looks like. So, this is gz times e to the something is positive, right. So, e to the x square minus y square minus 1 by n. This is still bounded, right, because as y goes to infinity meaning you are either going in this direction or going in this direction. That will go to 0, right, because of e to the minus y square. What happens to x? X is between 0 and 1, it does not do anything, right, it stays bounded. So, this is a function which will go to 0 at infinity. Okay. So, this goes to 0 as mod y goes to infinity. Okay. And what happens at the boundary lines when x is 0? Well, when x is 0, I still have e to the minus 1 by n, does not do anything, it is less than or equal to 1. At x equal to 1, well, I will have 1 minus 1 by n. So, that also does not do anything, and there is an e to the minus y square which stays as it is, right. So, the function, the new function gn is bounded by 1 here, bounded by 1 here and goes to 0 inside. Since it goes to 0 inside, I can take a large square, right, such that it is less than 1 here, less than 1 here, right. So, let us write it down again, okay, maybe draw the picture here. So, I have 0, 1. So, I can take a large square such that outside here and outside here gn is less than or equal to 1, mod gn less than or equal to 1, here also mod gn less than or equal to 1, right. This has nothing to do with n is fixed. Okay. So, repeat, gn is a holomorphic function which goes to 0 when y goes to infinity, right. So, after a certain stage is less than or equal to 1 here, after a certain stage is less than or equal to 1 up here. On this line it is less than or equal to 1, on this line it is less than or equal to 1, right. And on this line of course it is less than or equal to 1, similarly here it is less than or equal to 1, right, otherwise you go down. So, in the domain inside maximum modulus will tell me it is less than or equal to 1. Okay. So, by maximum modulus applied like this, mod Gn is less than or equal to 1, right. But this is true for every n, right. Whatever n I take, I may have to choose larger and larger squares, but the constant one is independent of n, right. It has nothing to do with any value of g or any value of n, because it is bounded by 1 on this line, bounded by 1 on this line, and goes to 0 inside. So, I take a large enough square outside, which is less than or equal to 1, on the boundary it is less than or equal to 1, maximum modulus tells me it is less than or equal to 1 inside. So, the 1 is an absolute constant you get, okay. So, the bound here is independent of n. So, I can let n go to infinity. So, let n go to infinity, what will happen? If n goes to infinity for any fixed z, this goes to 1, so I will get gz, right. So, this we get mod gz is less than or equal to 1, which is what we wanted, right. Remember, we defined this so that everything can be reduced to 1, okay, which tells me, implies the lemma. Okay. So, it is a simple application of the maximum modulus.